chapter 13. 잠깐만. Just a minute. Chapter 13 is identical particles. And the basic idea of the identical particle means all electrons and protons are indistinguishable. We cannot distinguish each kinds of electron and protons, and because they are same with each other, so we call it is indistinguishable property is important in basic elements of the quantum mechanics. So let's think about two spin have particles. And for two spin case and the spin up case and the spin up down case, or the down up case and the down case, and it can be write down the uncoupled basis as spin quantum number S1, S2, and the corresponding magnetic quantum number M1, M2. In coupled basis, here there are four kinds. One is that total spin equal to one case, and S equal to one case, and three possibilities, and 1, 1, 0, and 1 minus 1 case. But here S equal to 0 case, and only have the 0 case. It is a coupled basis. Is one case and the coupled basis as S and MS, corresponding MS. Here in the exchange operator, in the uncoupled basis, when you think about the spin up-down state, and we do not know that it is the first electron and the second electron, and it is first electron is up and the second electron is down, or the second electron up and first electron down, and we do not know. So, and which particle has a spin up and spin down, we do not know this specific situation. So it means that here it is indistinguishable. Distinguishable from the up and down up case. And so in this case, in other words, and this uncoupled basis is not appropriate for describing the particle system. It is uncoupled basis is not appropriate. So we should think about that coupled basis. And the coupled basis, for example, 1, 0 case, and 1, 0 means that total spin is 1, but here there are superposition can be possible. It is a 1 over square root 2, and up and down plus, and down up combination is also 1, 0 state. And also in the 0, 0 state, 0, 0 coupled basis is that 1 square root 2, and up and down and minus, and minus plus, and it is 0, 0 state. Then let's think about the particle exchange. Particle exchange from the first case is that 1 over square root 2, and also here spin up becomes down up, and the plus and up down combination because of the exchange between two particles, and up and down becomes that the down up, and down up becomes up and down. So because this plus case is the same with the 1 0 state, it is identical. It is identical case. But when you think about the 0 0 state and the 1/2 square root 2, and the up down becomes the down up minus, and the down up means that the up down. Then in other words, and let me here, when you compare with this term before the previous initial state, and the up down and down up case has the minus 1 upon square root 2, and the up down minus down up case. So in this case, we should keep in mind that the minus sign is coming from the pi phase shift. The pi phase shift. So then, so there are two possibilities. One is that identical, and when we apply the two particle exchange, and also one thing is that identical, but the other one is that minus sign appears in the phase shift case. So let's think about that exchange operator. Exchange operator P12. When you apply the P12 as a quantum state S1, S2, M1, M2 case, and the two particles exchange with each other, and so S2, S1, and M2, M1. So, in the Edison coupled basis, let's think about the coupled basis. Coupled basis case, P12 apply to the 1 0 state, then P12 apply to 1 0 state is that the uncoupled basis case, and the 1 over square root 2, and up down plus down up case, and the particle exchange is that as we see in the above, it is down up plus up down. So it is the same as the 1 0 state. Recall, and by adopting the exchange operator applies to the 1 0 state, and it is unchanged. Here we call it as a symmetric under the operation of the exchange operator. But when you apply to the P12 to the 0 0 coupled basis, and the P12 apply to the 1/2 square root 2, and up down minus down up, then it is that 1/2 square root 2 up down becomes down up minus up down. Then it means that it is minus sign appears, minus 0 0. Then here minus sign appears, we call it is antisymmetric. Basically, it means that here it means that 1 0 state and 0 0 state eigenstate of this exchange operator but with the eigenvalues in the 1 0 case plus 1, and the other one 0 0 case the minus 1 eigenvalue. So when you think that exchange operator applied to the 1 1 case, it is that the 1 1 case means that the spin up, then it is the identical spin up case, and it is a plus 1 eigenvalue. And the exchange operator 1 minus 1 case, one minus case is that the P12, and the spin down case, spin down exchange is that the spin down, and in other words, yeah, it is the plus 1 and the 1 minus 1. Also, it is a symmetric. And also in an uncoupled basis case, 1 minus 1 represent as 1 half, minus 1 half, minus 1 half case for the S1, S2, M1, M2 consideration. And so there are two kinds of state for the symmetric state and the anti-symmetric state. Then from this basis, and the Pauli exclusion principle is appeared. We already know that the Pauli exclusion principle is the, we already know this from the modern quantum mechanics. And there are two kinds of particles. One is the bosonic particle, and the other one is the fermions. And the bosonic particle can occupy as many particles can reside in the same quantum state. But in the fermion case, and only one or two particles can be reside in the same quantum state by considering a spin. So, and it coming from the exchange operator in the symmetric and antisymmetric case. And let's think about the eigenstate. Eigenstate of the exchange operator. And the psi plus minus. Then the probability of finding some final results. And the probability to find the psi in the final f, psi f means that the final quantum state, and the eigenstate at first, and the eigenstate observed in the final quantum state, and the probability means that the absolute square. So let's think about that probability of the exchange of two particles. And the probability of the exchange two particles applied to the psi eigenstate becomes to the final quantum state. Then it is that absolute square and the psi f and the operator P12 operation to the psi plus minus in absolute square. Then, and the energy eigenvalue can have the plus minus. So, and psi f, and the eigenvalue can be plus minus 1, and the psi square. Then it can be write down as the psi f and psi that is the same with probability from the psi eigenstate to the final state. And it means that in experiments cannot distinguish between the systems with identical particles exchanged. And also, by applying the it is the same, and by applying the two particle exchange operation, it is the same with the probability without exchange. So in experiment, and we do not know that the particle exchange or not exchange. So this kind of coupled basis proposition are promising representation of identical particle system. And here I write down in words, and cannot distinguish between exchange and unexchanged system. So here, for example, and here 1 0 state and 0 0 state, and here this represent one particle spin up, and the other particle and spin down. But here, this 1 0 state and S equal to 1, and 0 0 state is that the total S equal to 0. So, so in this case, and there are symmetrization postulate. What is the symmetrization postulate? And the quantum state vector of a system must be either symmetric or anti-symmetric with respect to exchange to particles. And here, and for example, when the for on exchange of two particles, and in the case for the symmetric state, we call it a boson. The boson has an integer spin, and symmetric state. And the fermion, it is a half integer spin, and it is antisymmetric state. We already know this, but we should keep in mind that here total wave function have two parts. One is that the spatial part, and the other one is the spin part. And the spatial part and spin part wave function can be separated. And here, in the case of boson case, bosonic wave function has two possibilities. One is that the symmetric case means that here spatial wave function also symmetric, and the spin wave function also symmetric case. But in for boson case and the antisymmetric case, and the spatial part antisymmetric, and the spin part antisymmetric, then basically, and it's a total wave function also symmetric. In fermion case, and the total wave function is antisymmetric, and here psi fermion case and symmetric antisymmetric combination is that the spatial part is symmetric and the spin part it is antisymmetric, and psi fermion case and the antisymmetric symmetric case is that the spatial part is antisymmetric and the spin part symmetric case. Then it also total wave function is antisymmetric. So then the symmetric wave function or the antisymmetric wave function, and there are two kinds of particles. So here in this chapter we deal with a symmetric and antisymmetric wave function case.